This video is going to be going over the origins of this thing called the golden ratio. And the next video will be doing some questions that deal with the consequences of the golden ratio. Now, I want to start off just by talking about some of the things that are usually associated with the golden ratio. A lot of people are familiar with the golden spiral, which is a shape that is associated with a lot of things, including seashells and galaxies and waves in the ocean, and all sorts of things around the human body. And it's got kind of a reputation for being everywhere in nature. And this is true. There are a lot of things in nature that have the golden ratio in it. For example, some people will say that this rectangle around this size, the size of dimensions of a credit card on there, is the most beautiful rectangle that you can have, because this side here, if this is 1, then this is going to be around 1.618, which is this golden ratio difference between the sides on there. So some people will say that this is the most aesthetic size that a rectangle can be. And if you fit the human eye in there, that's the ideal shape for an eye. Or if you have the shape of the human brain, right? Maybe it's covered on there. Or even if we make that a vertical golden rectangle, maybe this is the ideal shape of a nose, right? But I've also seen in the video that I posted, you've also got this host going over all the golden ratio elements that are in the arm. So maybe this is 1.6 times as long as this thing here. And then when you get down to the wrist and the fingers, this is also another golden ratio representation. Then along the finger, there's another golden ratio inside of that. And a lot of this is sort of overblown, right? A lot of this talk about the golden ratio, there's too many things that are attributed to it. Just as an example, in that video that I posted, if you pause the video and actually measure these things that are supposedly 1.618, in relationship to each other, not a single one of those is 1.6 in terms of its proportions. A lot of them are 1.4 or closer to 1.8. But even a quote-unquote ideal figure, which is kind of a silly notion in the first place, an ideal proportion, 1.6 is not even the average of human beings, or even a particularly pleasant ratio to look at for all these things. So you could build just as good of a human being with using 1.5 or 1.8, right? There's nothing special in particular about this 1.6 in terms of the human body, right? Lots of mystical, attributions have been made to, for example, the number of white keys in an octave and black keys in that same octave. That's 8 to 5, which is around 1.6, which is not even close to our actual golden ratio. So to spoil this golden ratio here, I'm just going to tell you what this is, and then we'll talk about how we arrived at that number. The golden ratio, we use this Greek letter phi for it. And this is our golden ratio. The exact number, so the exact number is 1 plus the square root of 5, all of that divided by 2. But what that ends up being is around 1.618. So anytime you're using the golden ratio, I might use this Greek letter phi, but in your calculator, I think 1.618 is a good approximation of that. It is one of those numbers like pi or square root of 2. It's an irrational number that will continue on and on forever. But we'll use 1.618 when we do our calculations on here. And I want to talk about how we arrived at that number. So in order to talk about how we arrived at 1.618, we need to talk about sequences. So sequences are ordered lists of numbers that we call terms in this context that follow a predictable pattern. So I'm going to write some sequences here. If you're taking notes along with this one, then leave some room over on the right hand, or both the right and the left hand side, so we can talk about them. Okay, so if we look at this first sequence, obviously the pattern here is that we're just counting up. So the next term would be 7, right? Predictable pattern tells us that we could say the next term is 7 here. But the pattern here is that each time we're adding 1. In this next pattern, we take the previous term and we multiply it by 2. So that would give us 64, 128 for our next terms. For this one, each time we're going to be adding 4. And for this one down here, we could think of this as each time we're dividing by 2. So 2/3 to 1/3, we would divide by 2, and then dividing by 2 again gives us the next term. So this would be 1 over 24, 1 over 48 for the next terms. But we want to think about this in terms of multiplication. So I'm going to say this is times 1/2. All right, that's how we get the next term on there. So sequences where we add or subtract. To get the next term are called arithmetic sequences. And sequences where we multiply or divide. These are called geometric sequences. So looking at this one here, this is going to be arithmetic. So it's geometric, arithmetic, and geometric. We also have these terms for this number here. This number that we're adding every time, this is what we would call a common difference. Right. If I add that one common difference, if I add 1 to the previous term, that'll give me the next term. In the context of geometric sequences, this is called a common ratio. All right, so the common ratio for this sequence would be 2. Common difference for this one would be 4. Common ratio would be 1/2 for this one here. So that helps us develop a predictable pattern, and those are two types of patterns that we can have, either adding or subtracting some number, or multiplying. A third type of sequence is called the Fibonacci type. And the terms for this one, here's an example of this, would be 1, 1, 2, 3, 5, 8, 13. The rules for this one, we don't have a common difference or a common ratio, so it's not arithmetic and it's not geometric. I'm just going to move that down. So it's not arithmetic, it's not geometric, it's something else. And you may have seen this before already, but the pattern here is we take the previous 2 terms to get the next term. So we can see that, for example, 2 plus 3, if we add those together, that gives us the next term of 5. And similarly, if we add 5 and 8 together, that's going to give us 13. So the next number in this sequence is going to be 8 plus 13 would be 21. We can continue the pattern there by just adding the previous 2 terms. So for a Fibonacci type, we add the previous 2 terms. To get the next term. Here's another example. So for this one, it's unique that we have to start off, we have to name the first 2 numbers. So traditionally we would use 1 and 1. But if we started with something like 10 and 12, we could continue the pattern by adding 10 and 12 to get 22. 12 plus 22 is going to be 34. 22 plus 34 is going to be 56. And so on. So that is also considered a Fibonacci type. One of the uses for this Fibonacci type, or something that you may have seen, is if you take these numbers in order and you make squares that have those dimensions. So let's say I make a square that is 1 by 1, and then I'll make another square that's also 1 by 1. Then the next item in that sequence is 2, and I can line that up right next to this one just because 1 plus 1 is 2, and then I can continue this pattern of making squares. So, right, 2 plus 3 is 5, and that'll fit exactly into here. There's an 8, and then finally I'll make roughly a square that's 13 on here. So we could continue this pattern as long as we wanted to on here, but this is the basis for what people will call a Fibonacci spiral on here. So the way that we would draw that is we can start and just kind of use the corners of these squares as our design, and that will give us a nice curve that goes around making a particular pattern. And this is the type of pattern that people will say you can see in all kinds of things in nature. Salvador Dali really liked to use, and other famous artists like to use this golden ratio as a style for their composition, right? When they're making their paintings, they may, draw something, maybe the eye of the particular subject goes here in the center, and then they're in a capsizing boat or something like that. Anyway, if you are looking for some composition inspiration, this has certainly been used. So we have 3 types here of sequences. We've got our Fibonacci type, we've got our arithmetic and our geometric, and you may wonder if we can combine these at all in any way, and I'll spoil it and say there is one special sequence that is both geometric and is a Fibonacci type. If I look back at my Fibonacci sequence, I'm just going to write out a few more terms here. So let's see, the next one would be 34 and 55, and I'll do one more, 89. So this sequence is Fibonacci type, right? You add the previous 2 terms to get the next term. But if I think about what I need to multiply in order to get to each next step, here I'm multiplying by 1, then I multiply by 2, and then I multiply by 1.5, and then I multiply by 5/3 is going to be 1.66. And if I continue going with this pattern, when I'm multiplying from here to here, I'm actually going to be multiplying by 1.618. So there is a relationship, and that's technically 1.1618 repeating. And if I continue making terms on here, this number, what started at multiplying by 1 and 1.5, this will actually get closer and closer and closer to this number 1.618 and so on and so forth, where we end up with converging on this number here. So if we had an infinite number of terms, we can just use this golden ratio number. So I'll go ahead and write the sequence out. This is 1, and then the next one would be 1.618. And I'm going to use a common ratio of phi. So this is going to be times phi. And then times phi to get the next term. That's going to be 2.618. And then if I multiply that again, times phi, then I'm going to get 4.236, and we could continue with this. So we know that this pattern is at least geometric, but something to notice when we do this, when we start with 1 and when we multiply by phi, look at this third term here, 2.618. This is also Fibonacci type, right? 1 plus 1.618 is going to give us 2.618. And this next term, 4.236, is also what we get when we add these two terms here. And that pattern is going to continue all the way, if we continue multiplying by this phi, we could say this is, right? It's definitely geometric, and it's also Fibonacci type. Now, the fact that it's both of these together, it's both geometric and Fibonacci type, means that we have a really interesting relationship between when we multiply and when we add. So this is something that shows up in nature a lot, because there are times when sometimes you need to grow in terms of area, right? So that's sort of like a multiplication type of thing. But you need to be adding new elements, let's say like the new seeds of a flower. That's more of an addition thing. So when you need to sort of strike a balance between growing and adding things on here, this golden sequence, right, which is what we have here, this golden sequence, or using phi as our common ratio here, that's going to give us something that is expressed in nature a lot. The most common thing that you can see expressed in nature is when you talk about something called the golden angle. So the golden angle is an answer to the question, what if we split our circle, which is going to be made up of 360 degrees, into two parts, such that the larger part is phi times bigger, and the smaller part so that would look something like this, where we have a circle and the whole thing is 360 degrees, but what if we split it up into two pieces where this is kind of our short part over here, and then we want to split it up so that our large part is 1.618 times bigger on there. So this is our small angle, this is our large part over here. This small part over here, if we want both of these to add up to 360, this is actually going to be around 137.5 degrees. That's going to make this one 222.5. But we use this one, 137.5, and we call that the golden angle. Now, the way that this can be used is if you look at the packing pattern of seeds in, let's say, a sunflower seed. This also applies to pine cones and pineapples if you look at the segments on there. Let's say that you were trying to fit the most seeds that you possibly could inside of this circle here, this pattern here. If you just sort of did something like this, right, kind of picking a pattern like that, and then, you know, maybe you can add a few more on here. You can get a decent number of seeds on here, but you can see that there's, like, you know, not a lot of space in between this seed and this seed over here, and there's a lot of room in between here and here that's not being used. So we could, you know, maybe just keep fitting seeds inside of here and maybe get a few more seeds, but eventually they're going to be too crowded on there. So that would be one way to try and fit in a bunch of seeds in here, but I'll use another technique that uses this golden angle of 137.5. So I'm going to start here. My first seed is going to be right there. And then what I'll do is I'm going to go, so I'll exaggerate it for a little bit, but I'm going to go out by some set distance, and then I'm going to rotate by that golden angle over there. So I'm going to go out and rotate by that golden angle, and then place my next seed there. And then I'm going to go out again and rotate by that golden angle again, and place my seed out there. Okay. So if I do this, kind of not going out so far and just staying, actually I'll leave that up here so you can kind of see what the idea behind it is. So if I start to do that pattern a little more subtly, where I go out a little bit and rotate 137.5, and then I go out a little bit more and I rotate 137.5, so that'll probably put me around here. So out a little more, rotate 137.5. Sorry, I'm just thinking a little bit about what I want to, where these should go. Okay, so out here, and then you can start to get this pattern forming if you follow that. But if I follow that same pattern over and over and over again, I start to get something that I'm not representing perfectly here, but you start to get these sort of spirals that show up. Like you could even trace them. Do this next time you have access to a flower that you want to see, but you start to get these sort of spiral patterns coming out of this. But what you end up with is the most efficient way to pack all these seeds, as many seeds as possible, into just one circle on there, right? So nature has found a way to sort of think about how do I add seeds as well as grow, kind of giving them as much exposure to the sunlight as possible. And you'll even see this with flower petals, right? Like you want those petals to be exposed to as much sunlight as possible. And so the way to do that is to have this golden ratio using the golden angle set up so that you can get as much exposure, as many petals as possible, doing as much photosynthesis as possible, collecting as much sunlight as possible in an area on there. A less fun application of this you can see in some shower heads. They will use this pattern on there, or drainage, just like little drain covers if you want to have as much water going through this while maintaining the integrity of that drain that's going through on there. Some other applications that you'll see of this, there's a architect, Le Corbusier, which I think is his nickname, stands for the Crow on there, but he was an architect that really enjoyed making things that he called human-centric. So one of the things that he would do is, he said, if you were designing a room, using this standard measurement system on here, if you wanted to incorporate the golden ratio, which he considered a very human-centric, or kind of a nice humans, a measurement system that was based on humans, we know that we can't really use 1.618. That number 1 plus square root of 5 over 2 is going to go on forever and ever and ever, right? So trying to locate that on a traditional ruler is not going to be ideal. So what he devised instead, he actually has some measuring tape that you can go and buy on there, but he used something that goes a little bit like this, where he says, let's start with 1 and then maybe make this next one be 1.618, and then add those two together to get 2.618, and then add those two measurements together to get this on here, and then made some additional measurements on here where he proposed a golden ratio kind of set up within each of these measurements on here, so you could split that 1 up into some measurements that looked like this. But what you would end up with was what he called these human-centric measurements on here that he believed, actually this would probably go quite a bit further on here, but he believed that if you used these measurements to design a room, that you would have something that was closer to what humans naturally appreciate. So you can check out the Wikipedia or look at some of his work that was based on the golden ratio. Another big one was if you think of the old Pepsi logo. I'm old enough to remember when Pepsi had this logo, and then at some point they changed it to look something like this, right? And there's a really funny, it's an interesting document to read, but the person who designed this new logo spent about 37 pages describing, since the dawn of mankind, people have wanted to design, and this is, the progress of humanity represented over here. But the point is they used a lot of golden ratios in order to, circles that had radiuses that are proportional to the golden ratio, and composition wise, right? Maybe you can split this up into, some golden ratio type setups on here. But in any event, somebody was paid a lot of money to base a design around some theme, and the golden ratio is just a really great theme for that. Lots of logos. I think Twitter is maybe the most infamous one, where I've kind of, rest in peace to Twitter, but the logo didn't quite look like that, but each of the circles that were used to design that had a specific ratio idea behind each of them. It's not necessarily the best in universally decided best ratio to use for any rectangles that you have in your design on there, but if you are looking for sort of a theme to develop a room layout around, Corbusier is a big fan of taking these golden rectangles where this long piece is where this long piece is 1.618 times as large as the short piece, and if you use a combination of squares and golden rectangles, you can get something that fits together really nice. You'll end up with some designs that kind of play with that idea of addition and multiplication being really nice, and you can kind of make a interesting composition, interesting room layout, things like that. So the last thing I'll do is talk about a type of question that I might ask on the exam dealing with golden rectangles. So golden rectangles have a short and a long side on here, and the rule is that this long side is always going to be equal to the short side times phi. Right? So if you have, let's say this is, for example, if the short side is 3, then this long side would be 3 times 1.618, or 3 times phi. Another way to think of this is that the short side, let's say you have the long side, the short side is just going to be the long side divided by phi. So let's use this to solve a problem on here. So I've got one in mind for us to work with. So we'll say following layout. Consists of 5 golden rectangles. And I'll say our goal is going to be to find the of the entire layout. So I think I want to do this all on one page here. So I'm going to move this down here. And that layout that I'm talking about is going to look like this. So here's my, I said I have 5 golden rectangles here. So here's one golden rectangle. There's another golden rectangle. I'm going to size these up so they line up with that there. Okay. So 1, 2, 3, 4, 5 golden rectangles. And I'm going to say if this measurement here is A, we can assume that measurement there, A, is equal to 1. So we want to find the area of all 5 of these. And if I start making some, if I start making some new markings on here to kind of think about what my measurements might be, let's call this part B here. We can call this measurement here C, and then this over here, we can call that thing D on there. So if all 5 of these are golden rectangles, right? I know if A is 1, then this measurement here, so we can say B is going to be equal to A times phi, right? The long side of this rectangle is going to be phi times the short side, so that's A. Kind of skipping ahead to D over here. D, we don't need to use the golden ratio at all, really, to find this. We can say that we've got 1, 2, 3, 4 of these A's is the same as D. So we can say this is 4 times A on there. And then this relationship between D and C, well, this whole thing is a golden rectangle. D is the long side, C is the short side. So it must be true that C is equal to D divided by phi. So using this, using our measurement that we have here, A equals 1, we can figure out these lengths. So A is going to be equal to 1. B is going to be equal to 1 times phi, which is around 1.618. D is going to be equal to 4 times A, which is 4. And C is going to be equal to looks like 4 divided by phi. So I'll punch into my calculator 4 divided by 1.618, and that's going to give me 2.472. So now I have my dimensions. I know what A is, B is, C, and D. That's all these numbers here. The area for the whole layout, one way I could do this, I could figure out this area, add 4 of those, and then figure out this area and add them. But I think it's more efficient to just think of this as being one big rectangle. So this is going to be one measurement over here. I'll call that the length, and this whole measurement here, I'll call that the height. For our final calculation, my total area is going to be equal to that length times my height, which is the same as, so my height is going to be, or I'll start with my length, right? So C plus B. And my height is going to be 4A, or that's the same as D over here. Give myself a tiny bit more room to finish this up on one page. So that's going to be so in parentheses, make sure we're keeping that in parentheses there. C plus B is going to be 2.472 plus 1.618. That whole thing gets multiplied by 4. So our final answer for what is the area is going to be 2.472 plus 1.618. That's going to be 4.09 times 4 is going to be 16.36. Something I do want to point out before I wrap up this video is that sometimes when you combine these golden rectangles on here, people will think that there's some information missing from this, or they will assume that this whole thing is a square. Now, we can't make that assumption. It turns out that this height here is 4, and this length here is 4.1, just about. So we shouldn't ever make the assumption that this whole thing is a square. In fact, that's going to be one of the wrong answers if you're given multiple choice on there. So for questions like this, just use the fact that we have it's made up of golden rectangles. Use those relationships to come up with your dimensions, and that should be all you need. All right. The practice exam is up on Canvas if you want to take a look at that. But I will answer any questions that you have next class, and good luck.